Permutation channel importance is an explainable AI method, good for gaining one insight, and that is which channels in a computer vision model are most important. When dealing with normal RGB images, the insights that this method can bring are limited. But when we move to remote sensing problems that typically use more channels as input, then the method can become more useful. Hi, I'm Connor and welcome to ADO. Today we are going to walk through a Python implementation of PCI. Technically, this method can be applied to any predictive machine learning model. In this video, we are going to apply it to an image segmentation model trained on multispectral images. Now, if you're not so familiar with remote sensing data, don't worry, I'll explain what multispectral means in the next section. Before we begin, I'd like to mention that this is one of the first lessons in a wider Explainable AI course for computer vision that I'm working on. The course is going to be completely free and open source, and I'll chat a little bit more about it at the end of the lesson. For now, you can already find the article for this lesson in the description. This is actually the second part of that lesson, and you'll find a more detailed description of the theory behind PCI. The article also includes all the code and links we discuss here, and it should be useful if you miss some of the finer details that we discuss. We're going to be working with the Landsat Irish Coastal Segmentation Dataset, or LICS for short. Specifically, we'll focus on the test set, which includes 100 images of the Irish coastline. For each image, we have a target, which is a binary segmentation map that classifies every pixel in the image as either land or ocean. We also have 7 spectral bands. These include your normal RGB channels that you will find in any image. But this image was taken by a NASA satellite with advanced sensors, so it also captures channels or bands that are not visible to the human eye. For example, we have infrared bands like the near infrared or NIR band. NIR has been shown in more traditional remote sensing research to be very useful for water body segmentation problems. And so we'll come back to it at a later stage in this video. Okay, so let's move to the notebook to take a closer look at the LICS dataset and the model that we are going to explain. Now, we are working in the Permutation Channel Importance notebook in the Permutation subdirectory. So we have our imports, and we have some pretty standard Python imports. We're working with PyTorch, so we import that package. We're also going to download our model directly from Hugging Face. And then in this last bit, we navigate to the modeling directory, and this allows us to import the segmentation dataset class from the dataset's Python file. And this is the same dataset class that was used to train our model. So when we import our data using this class, it just formats it in the correct format for inputs into that model. Okay, so next we load all of the paths for the LICS test set, and you'll have to download this data set yourself. You can see that we have 100 images in the test set. So yeah, the next step is to create a dataset object using that segmentation dataset class that I mentioned. And to do that, we just pass in the list of paths, and all like the data formatting and data loading is done by that class for you in the background. We're just going to load the first instance from this data set, and the getItem function of this object will return the bands and the target variable, or in this case, the target is a image segmentation mask. So let's just look at the shape of the bands. And Yeah, in this case, we have 7 spectral bands, and each of those bands is a grid of pixels, which is 256 by 256 pixels. So let's just actually visualize each of those bands, as well as the target variable. Don't worry too much about this code, it just creates this visualization for us. And you can see we have our target variable, which is an image segmentation mask, and each of these 7 spectral bands. Okay, we'll come back to this visualization in a moment, but for now, let's get a prediction on this instance from our model. So like I mentioned, we're going to download our model directly from Hugging Face. And this model was trained on the LICS training set. Well, actually, it was trained using a 2-step process where it was initially pre-trained and then fine-tuned. So using a transfer learning approach. And yeah, this is the model that gives us the best performance on the LICS test set. So we get our model path from Hugging Face. We then load this model using PyTorch, and we then move it to a GPU. Now, I'm working on Mac, so I'll use an MPS device. You should use MPS or CUDA if you can. Otherwise, if you don't have a GPU, then CPU will still work. Just keep in mind that the code will run much slower. Then the last step is to set the model to evaluation mode. And yeah, we can take a quick look at the model kind of architecture. And you can see we are using the UNet image segmentation architecture, which is a very common and popular architecture for image segmentation. Okay, so now let's get our model's prediction on this instance that we just saw. So to do that, we move the bands to the GPU. We then add an extra dimension for the batch, because typically the model will receive images in batches. And in this case, the value for that first dimension will be 1, because we only have 1 image. And then we input that formatted bands into our model to get an output. So let's just take a look at the shape of the target and the output before we visualize it. And you'll see that the value for the first dimension is 2. And this is because we are dealing with 2 classes, water and land. So for example, the target variable will contain 2 binary segmentation masks, one where it treats land as the positive class and another when it treats water as the positive class. Similarly, the output will contain 2 sets of scores or grids of scores for our 2 classes. So to account for that, we use the argmax function, and that will just give us a 1-dimensional grid of pixels for both our target and output. And for example, for the output, we will take the class that has the maximum score. So every pixel will be classified by the class that has the maximum score. Okay, so now let's just visualize those and see how the model is working. And you can see that the prediction, which this is the sort of predicted image segmentation mask that the model gives us using those 7 bands as input, you can see that it is very similar to our ground truth or our target image segmentation marks. It might just have missed some of the kind of granular detail in the close line. But overall, we can see that 99.7% of the pixels have been correctly classified. So yeah, this value in the brackets here is our accuracy score for this specific prediction. Now, to give you an idea of what's going to happen when we start permuting the different channels, let's go back to that input that we saw before. And now what we're going to do is we're going to shuffle one of those bands, and specifically the NIR band. And to do that, we first select that channel, which in this case it's always going to be the third channel in an image. Then we convert this to an array. We then flatten the array because it's going to start off as a two-dimensional grid of pixels. We just want this to be one long array. We then shuffle all of those pixels. And then finally, we resize that shuffled array of pixels so that we go back to our original grid of 256 by 256 pixels. And the last step to do is to just replace the original band with this permuted band. So we can run that. And yeah, let's just take a look at what the input looks like now. And you can see that all of the bands are exactly the same, except that the NIR band is sort of randomly shuffled around. And yeah, we can do the exact same thing, get a prediction with this permuted image, and you can see, okay, wow, it's obviously not predicting the coastline well at all anymore. So this tells us that the NIR band was important for predicting the image segmentation masks for this instance. If we repeat this process for all of the images in our dataset, for all of the channels, we can understand which channels the model is using to make predictions in general. So to do that, we have a few functions. So the first one calculates our performance metrics, and it takes in a set of targets and predictions. We can also define the type of problem we are working on. So yeah, technically PCI can work for any predictive machine learning model. I've got this code to work for classification problems, and in that case I use the accuracy metric, and it also works for segmentation, obviously, because that's what we're doing right now. And in this case we use average accuracy. And we use average accuracy because, just remember, each of these individual predictions will have their own accuracy score. And yeah, so this average accuracy calculation will loop over all of the targets and predictions, calculate the individual accuracy value, and then at the end just take the average of all those individual accuracy values as our final performance metric. The next function will shuffle a given channel in an image. And yeah, this essentially does the exact same thing that we saw earlier, this code that we went through when we shuffled the NIR band. This function does the exact same thing, but sort of in a more generalized way. So the last function will get the performance metric for the model with permuted data, where we permute one of the channels. And yeah, this kind of also does a similar thing to what we saw before, where it gets model predictions, except now we are looping over the entire data set. So we pass in the data set, we create a data loader of batch size 1, and then we iterate over every image and target in our data set using this data loader. And yeah, then we kind of get the targets, get the predictions, and finally, right at the end, we use the full list of targets and predictions to calculate our performance metric. And you might notice that there is the option to calculate the performance metric on unpermuted data, or just using our original images. And this allows us to calculate a baseline performance score. And yeah, essentially this is just the average accuracy on the LICS test set when none of the channels are permuted. You can see that we have an accuracy of 98.5%. So let's just do the exact same thing, but this time we are going to shuffle channel 3, which is the NIR band. And if that previous example is anything to go by, we should see quite a large decrease in the average accuracy when we permute this channel. Okay, so you can see that the average accuracy is now 60.5%. This means that when we permute the NRI band, the average accuracy decreases by 38.1%. And this is our PCI score for this band. It's just the baseline accuracy less the accuracy when we permute the channel. So yeah, the next step is to kind of just repeat this process, but for every channel in our inputs. And for every channel, we also repeat the calculation 3 times. And this is because the permutation process adds a little bit of randomness to the calculation. So we repeat the calculation to get a more stable estimate of the scores. So I'm going to run this code, and it's going to take a while, so I'll see you in a minute. Okay, so you can see that took about 3 minutes. I'm not sure if you can hear the laptop fans, but this little GPU was working hard. The final step is to just visualize those PCI scores. And you can see straight away that the NIR band is the most important. And this is followed by the SWIR2 and SWIR1, which stands for shortwave infrared bands. Now, these results are actually quite interesting. In traditional research, where researchers try to apply deterministic methods for water body segmentation, you find that these NRI band and the other infrared bands come up quite often. And so what we see here is that the model is using spectral bands that are consistent with sort of previous research. This is one of the benefits of explainable AI, or PCI specifically. And that is, through explaining the model, industry professionals are more likely to trust it, especially in this case when the model explanation aligns with their domain knowledge. From a computer science perspective, it also has benefits because it may allow us to reduce the complexity of the model input. For example, we can potentially train a model on only these 3 important channels. And as a result, we can simplify the model input and reduce training times. I would recommend trying to apply this method to a different data set. And in the notebook, you'll actually see it being applied to a pot plant data set, which is an image classification problem. Like I said at the beginning of the video, this is part of a wider XAI for computer vision course. I also plan to cover methods like SHAP, grad cam, and deconvolution. And if there's anything else you'd like to see in the course, please let me know in the comments. There will be an option to buy an ebook if you want to access the course content offline. And there will also be a paid version of the course where you will get the ebook for free, a certificate, and you can watch all of the videos ad-free. If you want to support this work, you can get that course right now and you will get all of the benefits in the future.